Hello and welcome to KMeans Clustering, explained for beginners. I'm your instructor Kashif Murtaza from AI Sciences, and in this video we are going to talk about K-means algorithm, in particularly what is the result of K-means, what it does, and how does K-means achieve that result. So how does K-mean do it? And then we will see a better initialization strategy, sometimes known as K-means plus plus. And on the application side, we will see a couple of applications in the domain of image compression and dimensionality reduction using K-means. We will finally wrap up our video using K-means implementation in scikit-learn in Python. Before moving on, if you are new to AI Sciences, at AI Sciences we deliver a lot of consultancies, a lot of services, online courses related to artificial intelligence and data science. And if you are already our regular viewer, then be ready for another exciting video in the field of artificial intelligence and data science. So let's start. So first of all, let's focus on what does K-mean do? What's the result of K-means? So think about two-dimensional data. Let's say we have two features, feature x1, let's say, and another feature, let's say x2. Let's say we have two features. And these are all different data points in those features. And let's say we want to group the data into three clusters. Here, we want to make the data groups, and we want to make three groups. And the criteria for making a group of data is that in a particular group, all the data points, they should be similar. And similarity here, we define the similarity that the distance between two data points is small. So in a group, all different data points in the same group, they are close to each other with respect to the notion of distance. Obviously, the distance itself has a lot of definitions and different kind of applications. What distance measure? What is that thing that is defined as distance? But assuming a very naive and sometimes very popular definition of distance, like Euclidean distance between two data points, no matter what distance measures you come up with, that will define similarity between 2 points or dissimilarity between 2 points. And based on similarity and dissimilarity, a group is defined. So a group or cluster of data contains all the points that are close together, that are similar, that are less dissimilar, or something like that, where the similarity or dissimilarity is defined by choosing the notion of distance. Here, for example, assume that we are just using the ordinary distance, like a distance in the plane, distance between 2 points, a Euclidean distance. So we think that this is one cluster because all the data points in that cluster, they somehow are similar to each other. And this is another cluster, and that's another cluster. One way of defining the similarity of different data points is that you compute the pairwise similarity. For example, you compute the distance between all the pair of points and then somehow add all the distances together to get the overall similarity. One way is to compute the overall similarity of the group is that. Another way is to come up with a representative point in the cluster, sometimes called the centroid of the cluster or representative points of the cluster. So come up with that. So fix, for example, a particular origin of a cluster, a particular point. Obviously, what should be a good origin for a cluster needs to be learned, but fix a point and compute the distance of all the points from that point. And that total distance should be smaller. If, for example, we have three clusters, we have to choose 3 points, sometimes known as 3 centroids, and any point that is closer to one of these centroids is assigned that cluster. For example, think about this particular point. This point is closer to this centroid as compared to this centroid and that centroid. So this point is assigned the cluster label like green label, or in numbers maybe the number 2. Similarly, if you think about this particular point, this is closer to this centroid rather than the other two centroids. So what K-means does is it come up with groups of data and it gives you the centroids depending upon how many clusters you want to make, and all the data is grouped or clustered or categorized or partitioned in a way that the data point that is closer to whatever centroid, that label or that group label is assigned to that data point. Now, one question is, how do we come up with these centroids, these representative points? So really, how K-means work, that is something that is related to what K-mean does. But the real question is, how does it do it? So let's focus on that. There are several ways of coming up with this algorithm, K-means clustering. One way is by the way, you have to first fix this value k. This k is the number of clusters. So for example, in this case, the clusters are 3. What you can do is you can randomly pick some of the data points, maybe some of the data points, and call them as your centers. For example, this is a centroid. Maybe you randomly pick another one, which is this one, and then maybe randomly you pick another one, which is this one, and these are the centroids. So you start with random initialization of the centroids of representative points. Then you compute the distance of all the points from all the centers and see which point is closest to which center. So for example, these all points, they are closer to this center, and these all points, they are closer to this center, and these all points, they are closer to this center. For example, here we have assigned the centers randomly in the first go. Once the initial partition has been done, then what you do, you pick each center, each cluster, and compute the average value or the centroid or the mean point. That's the new center. For example, the new center here might be a point in this feature space that is no longer a data point itself. For example, maybe this point. So compute the center. Similarly, compute the center of this cluster. Maybe that is this particular point. And compute the center of this cluster. Maybe that is this particular point. And after computing all the centers, just forget about the previous groupings and regroup the whole data based on the new centers. Then repeat the process until the centers are converged and they are not changing in different iterations. That's how K-means achieve these centers, because the whole goal is to come up with these centroids, the representative points. Once you have better or best representative points, then clustering is just one step, because then you just, for each data point, you compute its distance from all the centers or centroids, and then just assign it to one which is closest to it. So that's how K-mean does. But the real question is how to initialize these centroids in the first place, because in K-means, how you initialize the initial centers, that impact the performance, and sometimes K-means perform very, very poorly if the initialization is not very good. There are several ways of initializing this K-means clustering algorithm. One obviously naive ways is to just pick all the centroids in the very first iteration at random. But better ways also exist. One of the better ways of initialization is known as K-means plus plus. Don't confuse yourself with K-means plus plus like it's a very kind of different kind of algorithm than K-means. It is not. It is exactly K-means, but with a clever initialization. So you can think of K-means plus plus as K-means with a good initialization. And the initialization criteria, or the centroid choosing criteria for the very first iteration, is the following. Obviously, that is one better way of initializations, which work very well in practice. There are other initializations as well. But it turns out that in practice, if K-means is initialized by this particular criteria, which is known as K-means plus plus, it works really well in practice. So what is that criteria? Let's say you have to pick K clusters. You have to pick K centroids, which means you have K clusters to form of your data. So what you can do is you choose the first center or the first centroid uniformly at random from the data. So let's say you are given this data, a lot of data. This is a lot of data that is given to you. And let's say you want to pick 3 clusters. Let's say you want to make 3 clusters, which means you want to pick 3 centroids. So first centroid, pick at random from the data uniformly. Now, do not pick the second point at random, but based on the point or the centroid that has already been picked. One notion is, or one intuition is, to pick the second point or the second centroid, which is not very close to the first centroid, because then the 2 centroids, they may represent the same cluster. So the idea is to pick the point that is really far away from the first center. So for example, this one. I'll explain the further steps how the second point and third point, they're picked, but let's see first in terms of intuition what it does. So once you have picked the 2 points, you pick the first point randomly, uniformly, any point at random, but then you pick the second point which is not very close to the first point, and then you pick the third point which is not very close to the first 2 picked points. And that's how you keep on moving to pick the initial centers, and in practice that works very well. Let me explain some details of this centroid picking strategy. So you pick the first center randomly, then you pick the second point, let's say, and for each data point, so for each data point x that is not chosen yet, you compute the distance of that point from already chosen point. So think, for example, in this particular case, let's say you already have chosen this point, and now what you do is you compute the distance of all other points from this already chosen point. So these are the distance values of all the other points. Now every point has a distance value with respect to this. Let me call this as dx, which is the distance value. Let's say this is point x1, so this is its distance is dx1. This point is x2, its distance will be, let's say, dx2, and so on. Now build a probability distribution that has weighted probabilities proportional to these distances, which means if we want to randomly sample a point from the not chosen points, then the probability that a point will be chosen is higher if the point is far away. And that probability distribution as a heuristic also has some statistical derivations, is proportional to the distance, which is the square root distance of this particular point. So if the point is far away from the already chosen point, at least the square distance, so if this is the distance, this is the square distance. So the idea really is to pick a point that is at least as far away as the square distance from the square root distance from the already chosen points. For details, there is a complete paper in 2006 on KMeans++ that explains the details and the statistical convergences and further kind of deep divings inside the KMeans++. But the real idea is you pick a point. I mean, the idea to memorize is the following. You pick the initial point randomly, then you pick another point according to the probability distribution based on the distances from the already chosen point. Then you pick another point based on, for example, you compute the distance of this point from all chosen points that are already being centroids, and build a probability distribution based on the distance, which in the naive words, which in the simple words is the following. Pick the third centroid which is not closest to the already chosen 2 points, which can be achieved as the third centroid is far away from the second centroid which is closest to it. And similarly pick the fourth centroid and fifth centroid and so on. So that's one better initialization strategy in K-means. Although the interested readers, they are directed to see the details in the paper in 2006 that explains this K-means++. Now that we know how K-means works and what it can do, It has a couple of, actually it has several applications. Let me explain a couple of them. Image compression. In images, for example, the image has a lot of intensities. Normally, the 8-bit image has intensity values from 0 to 255 and is represented by 8 bits, sometimes known as 8-bit image. Assuming a grayscale image. In RGB image, we have 3 channels: red channel, green channel, and blue channel. Each channel is an 8-bit grayscale image. For details, please see our computer vision course. We have explained these images and its details there in detail. You can see the description, and there are links to those courses. So what one can do is, rather than having intensity levels, all 256 levels, what if we think that intensity levels are just 8? For example, we have only 8 intensity levels, from 0, 1, 2, up to 7. These are 8 intensity levels. One way of converting these 256 intensity levels and mapping them to only 7 of them is to cluster this data into 8 bins, or find out the 8 centers. For example, this one, that one. Obviously, those centers are found in color space, in intensity space. And then pick each color and see what is the closest center to it. And whatever the closest center to it, assign this particular pixel value, that color, which is the color of the centroid. In that way, at the end of the clustering, each pixel will be having the color of its center, and we have only 8 centers. So we have only, at the end, we will be having only 8 gray levels. And this is one form of image compression, sometimes known as color quantization. Another very powerful application of K-means is in the domain of dimensionality reduction. Assume you have a data which consists of a lot of features. So for example, we have this data. And let's say it has D features. So that's data, maybe a classification data, or maybe supervised or unsupervised learning data, whatever data. And we really want to wish to actually reduce the dimensions from D to down some number. Let's say D might be, let's say, 10,000s, and maybe we want to reduce the dimension to some value C, which is really small. Let's say 5, maybe. So there are several other ways of doing that, but one way is to just cluster this data and build 5 centroids. So let's say these are the 5 centroids: 1, 2, 3, 4, and 5. These are, let's say, centroids: centroid 1, centroid 2, centroid 3, centroid 4, centroid 5. And you did this using K-means clustering algorithm, and maybe you have initialized using K-means ++ or something like that. Now what you do is you build, so let's say this is x1, this is x2, this is x3, and let's say this is xn, original data point. And let's say this is the x hat 1 is the reduced dimensions data. What you can do is you pick your data point x1, you compute its distance from the centroid, and that distance becomes a feature here. That is just a number. Now you compute the distance of x1 from C2, and that distance becomes a feature, new feature. And now you compute the distance from C3, and that's another feature. In that way, you will be having 5 features because there are only 5 centroids. Similarly, you compute the 5 distances from x2 and make a reduced vector in terms of dimensionality, which is x2 bar, and so on. So that's one way of dimensionality reduction using K-means, and this is also unsupervised approach, and it has very good comparisons between among different unsupervised dimensionality reduction techniques. For example, interested readers are requested to see PCA, for example, or TSNE. Both have good comparison results with K-means dimensionality reduction. There are a lot of other applications of K-means in pre-processing, in initialization, particularly in dictionary learning and sparse coding. This simple looking algorithm has very, very, very powerful applications. We have just discussed a couple of applications here, but there are a lot. So before actually closing this video, let me show you a hands-on example of K-means on some synthetic data. So let's load some libraries or packages, make blobs for building synthetic data. K-means, we import that from scikit-learn. NP may be required somewhere inside. And then maybe for some plotting purposes, let's load the matplotlib.pyplot. Now, what we do is we make blobs or cluster of the data. So we have, let's say, we have 1,000 points, and let's say we build 1,000 points such that they should have 10 clusters, and the total, the dimensionality of the data, just for visualization purposes, we are making the number of features just as 2. So, and then we build a model, KMeans++, using the initialization criteria as KMeans++, and then the number of clusters being 10. That's what we do. And then what we do, we actually transform our data to the K-means labels using kmeans.fit, and we build a mesh grid of data and make an image form of the data just for visualization purposes. So that's what we do. Now what we do, we represent the whole data, as an image form, and we will represent the data cluster centroids in different colors, and the points, they are in different colors. So let's see. So for example, if you see that these blue points, they are initial data. Forget about these different colors. These are just the aesthetic appeal for visualization of the data, just to make the data, visualize the data in form of image. So one cluster is this one, which has probably have this particular span. Another cluster is this one, which probably have this particular span and this particular span. All the clusters, they are in the form of these white crosses, and they have a particular span. In this particular area, we have a lot of clusters. For example, 5 clusters, this cluster, that cluster, this one, that one, that one. Different clusters, different centroids in terms of the radii, they can have different quantity of span. So that is just one quick example of K-means. You can see the code in detail, and feel free to modify the code and play with this code, and also feel free to apply this code on real example if you really want. So that's about K-means. I hope you have enjoyed this video. Please leave a comment, like our video, subscribe our channel, and share this beautiful video with your friends so that they also get a good understanding of how K-means work. Hope to see you next time.